Great.
Okay, let's start. Hello, everyone. My name is Cristian Prieto. I am a senior query engine engineer. That's the mouthful. At Coralogics. Basically, I just write query engines and things like that. And I really love to be a developer. I've been a developer for 30-something years. As you can see, I'm just old. And first of all, thanks for coming to my talk. I mean, having all the other interesting talks about AI and how we are going to be with our job in the few years is pretty nice to see. And we are going to talk about the Atari 2600 development, but not from the point of view that we are going to develop a game on things like that. The first time that I did this talk was something like that. We are going to learn how to do it, and there are going to be references for you if you want to later just have enough time to just make your own. It's pretty entertaining. But it's just to understand how Neanderthals used to code, because I'm pretty sure they used to. Why? Why this talk? Why not is the first thing that I want to see. I really love to be a developer, and I really like to see in the past how things used to be done, and try to bring that knowledge, that experience, all those things back to my present, so I can take something of the pride of that people, and I just make my art, my craft better. But because, as I said, being a developer is awesome, right? But it's not about writing code. And this is one of the stuff that everyone always thinks that development is, writing code. But it's not. It's about solving problems with code. Sometimes it's not even code. But the framework that I want you to just keep in your mind during this talk is that you always solve problems with constraints. And sometimes the constraints are hardware, some others are time, and sadly, sometimes the constraint is management. And we are going to see all of that here. I feel that this has become modern development. Just 30 years ago, 40 years ago, we have very little resources when we write software. And now, and I kid you not, I've seen people complaining that 60 gigabytes of RAM is not enough. Right? We have, in where I work, pods running with over 40 gigabytes of RAM, 500 of them, and 24 CPUs. And sometimes we just wonder, do we really need that much? Right? Well, these are a database. Yes, in our case, we do. To understand all these constraints and see the context of how these things were solved and why they have to be solved, we need to go very, very back to the company that I really admire in those days. Well, not in those days, I'm not that old. The Atari company. So many years ago, Atari was founded. There are like certain stuff. It was founded in 1972. But the two founders, Bushnell and Dabney, decided to get together around 1967 with a brilliant idea. Sell pizzas. I kid you not, to sell pizzas. And they were like, man, but you know what would be awesome? To just attract people to a pizza parlor with this new thing called video games. And they start doing it. It was not very successful, but that gave them the idea to, okay, the pizza stuff didn't work very well, kind of. I want to remind you of Bushnell after Atari founded Chuck E. Cheese. Right? And they decided to try something new. What if, instead, we sell the video games to those pizza parlors? So they left what they have and founded their own company in 1972. Fun fact for a trivia, originally it was not called Atari. It's what called scenery. But they couldn't use the name because it was used by a hippie candle company. Right? And they decided, like, look, let's start making a game and sell it. And they did. They made Pong, the arcade machine. It's a very simple game. I don't know, I assume that everybody at least once in a while has seen Pong. It's basically emulated two people playing ping pong or something like that. And it's kind of boring, but in those days, it was the shit, man. Everybody wanted to just basically get Pong. Like, it was crazy. Apparently, there used to be like long queues, and the first Pong machine, was the owner of the parlor called Bushnell and said, like, hey, you have to come and repair your machine. And they were like, but what happened? Shit, it just broke. And when they went to see, the reason is that it had so many quarters, so many coins, that the machine just basically like broke the container of the coins, right, and caused a short circuit, right? Because they never expected that it would be this popular. And they were like, man, we have money here. We have to produce this shit in huge amounts. And they started. And everybody started like, hey, I want my piece of that shit. Because it was attracting people. And there were like queues for this stuff, right? But there was a problem. They didn't have enough people to make the machines. They couldn't satisfy the demand. And when you cannot fill the gaps, competitors will do it. And there was no IP patents on those days on that type. There was not like, hey, you are using my Pong idea. No, there were like pirate copies now of Pong, people making those machines. And Atari started losing money. They just, what do we do? They just paid another guy, Keeley. He was actually like let's call it the software engineer. And he developed a new game, Tank. We are going to see Tank later. But Tank was another big success. Tank was released in 1973. And it was another big hit. Now, Bushnell had a brilliant idea. Apparently it was Keeley, the one who came up with the idea. There was, hey, we have this thing that used to play Pong, and now we put Tank, and that stuff sold. Why we just don't do a programmable Pong machine? Something that we can just program, sell to everyone, they bring it to their house, money, right? It was a brilliant idea. It was not the first game console. That's actually like a myth, because there were game consoles in those days. But the difference was that if I want to play Pong, I need to buy the Pong machine for my house. This was, you buy the machine and we have games that works in that machine. The thing is, to make this happen, we need to make it as cheap as possible, right? So super cheap, please. So for that, to make everything cheap, one way to make it is buying the pieces in the store. Like literally just go to a store and say like, hey, give me this and that. In the same way that we now buy pieces for our Arduino or Raspberry Pi and make our own embedded devices. They wanted to do that, so it has to be pieces that you can get in a shelf. So how do we make a console? Well, the first thing that you need is the CPU. And that was a hard one. Again, this is 1974, 1975. Atari was released in 1977, right? What CPUs we have in 1975? Mostly two, very specialized. We have the Motorola 6800, that is a fantastic CPU. I love it. And the Intel 8080. that gave origin to the Intel machines that we have now. There was a problem, the price. The Motorola 6800 was $175, $74. That is around 1,500 Australians today, with inflation and all that stuff and calculations. And Intel was around 360. I found in other places that it says that was 380. But what's the requirement and the constraint that I said before? It has to be super cheap. So we cannot use this. That the story is linked to Motorola, because during the development of the 6800, Motorola had a department to make the chip cheap, to make what they were doing even cheaper. And they have a department, and the department was actually very successful. And they developed a 6800 that was way cheaper. But sometimes constraints are management. And management dissolved the team, because if people is already paying 175, why should I make it cheaper? And dissolved the whole team, and they were looking for a job. That there was another company that was doing chips for the Texas Instrument calculators. That company was MOS. MOS came up with the idea that they wanted to expand to the computer chip market and hired the whole team. And they hired more people for designing a chip that was cheaper than the 6800. And they produced two, after around 6 months or so, they produced two chips, the 6501 and 6502. That's where the number comes from. And the reason it's called 65, it was to confuse people that it was similar to the 6800. Right? So, it was a really cheap CPU. One important thing is that to make CPUs cheap, the way that it was done is that you you print the CPU on a die. So the smaller the chip, the more CPUs you can put in a die, and the cheaper it will be. So that was one of the success of the 6502. This chip, I love it. As you can see, my t-shirt. Has certain characteristics that are make it very special for the console. Additionally, that it was cheap. It's an 8-bit CPU. That means that the register, the internal memory that it has, is around 8 bits. Not around, it is 8-bit. It has a 60-bit address. That means that the total memory that you can handle in this CPU is 64K, right? That's where the name of Commodore 64 comes from, right? It has 40 pins. We'll see why the pins are important, but it's just basically where you insert the stuff. It was a long chip. And only 3 registers. Compare, for example, with CPU that was very cheap as well in those days. That was the Z80. The Z80 has 16 registers, for example, right? And it depends on who you ask, 56 or 55 instructions. It was not that simple. I can tell you more stories about how this was made outside, but we have to advance. And didn't have division or multiplication because nobody thought that you will need it. In the same way that most ARM chips do not support multiplication either, right? We are in 2025. The important thing that I want you to know here is that it has a frequency of 1.19 megahertz. We're going to see a few numbers here that will just be important for all of this. The instructions, 55 or 56, can take between 1 and 3 bytes. Important thing, remember, instruction can take between 1 or 3. And instruction can take between 2 cycles, that 1.19 that we saw, up to 7 cycles, from between 2 and 7. That probably means nothing for us right now, but you will see why it meant something for them. It was a fantastic, a very popular CPU after 1975. A lot of game consoles were made with that, not only the Atari 2600. The first two Nintendo consoles, the NES and the Super NES, used as well not exactly the chip, but a variation of the chip made by Ryko. A lot of personal computers, Apple I and Apple II, use it as well. And the Commodore personal computers as well, all to Amiga. Amiga used a variation of the Motorola. It's so popular that Bending Rodriguez used it as well, right? And one thing that surprised me is that even in the future, it's such a good CPU that Skynet uses for Terminator, for the T-80, T-800. How do we know this? That is a dump. This is from the Terminator movie. This is a dump of the memory in an Apple II that I already said, uses the 6800. It's so popular that even when it was made in 1975, you still can buy one. And it costs you around 12 euros in Germany. But at $25, it was still too expensive, because it's $25, man. So they just came and said, hey, can we do something here to make it cheaper? And obviously Moss says, fuck yeah. And they come up with the idea of the 6507. That is the same CPU, right? But way cheaper. I put $12 there, but they are people saying that because you just ask hundreds of CPUs, it could go as low as $5. That compared with the 380 for the Intel, it was cheap, right? The difference between the 6502 and the 6507 is that it doesn't support interrupts. You don't need it for a cheap console. For example, reset. You cannot reset the console. To that, you have to disconnect it from electricity. Yeah. It's smaller because what I said, the smaller the chip, the smaller the die, hence cheaper. But to make it smaller, you have to cut lines. So you only have 28 pins or 28 28 lines or pins where you put in the die, compared with the 40 that we had before. And you only have 13 lines for the CPU bus. What does that mean, those 13 lines? That you only have a total of 8 kilobytes of memory. And this is no RAM. This is total memory. This includes code. So code, RAM, all your mapping devices, everything is 8 kilobytes. You can do more than that. There are techniques that later was developed, but space was a thing. Remember that I said the instructions can take between 1 and 3 bytes? So this is why you constantly count the lines of assembler code that you are writing and sum up, because it could be the case that you actually have too much code. Think about that. So we will see a little more limitations later on how they overcame this. The next thing that you need is the chip that you need for additional stuff. It's like when you buy today a motherboard, you buy a motherboard for a CPU, and that motherboard has a chipset, right? The same happened in those days. And it's the additional stuff. This one was as well bought. It was sold by Moss, and it's called the Riot. And is known as well as the Moss 6532. It has other names, but overall, this is the one. You still can buy it as well today, right? And the reason we call it the Riot, sometimes they're called the PIA, PIA, is because it has programmable interval timers, like basically a timer. You are making a game, and some games need a timer. You have up to 4 timers, and the control for the joysticks. If you don't know what is a joystick, ask your parent. Right? Support for paddles and things like that. There are like more advanced controls. Unknown stuff, Atari actually released for the 2600 a keyboard that adds more memory and convert your Atari 2600 into a computer, a shitty computer. It only has BASIC. I have it, but it's cool. And another thing that the Riot provides is the RAM. Now we're talking about like the memory that we know everyone, but you only have 128 bytes of RAM. Yeah? So next time that you complain about 64 gig not being enough, remember this. They only have 128 bytes, and they couldn't even use all of it. Some of it was reserved. The saddest part is that that was plenty of RAM. That was not actually your problem. Now we start talking about problems. We have the CPU, the initial controllers. Now it's time for the video card, right? There were no video cards. It's not like today that you just hopefully go and buy NVIDIA RTX. No, well, now it's as difficult, I guess, that it was in those days. But they have to come up with something. This is the only component that they have to do from scratch. And it was known as the TIA. It was made by Jay Miner, and the quote is, it was made by love. It's from his book. He says that he put a lot of love into it. It just took him between 6 to 7 months. He made it in a giant breadboard. If you don't know what is a breadboard, that's a breadboard. But it was giant. I read in one of his books that the breadboard was 2 meter size, like 2 by 2. It was giant, because there was nothing there. And I just imagine just tinkering with the stuff that you have to put there, right? There is no video RAM. So video RAM is like, you buy your video card and you put just shaders and stuff there. There was no such thing there. You have around you need around 30K for this price in those days. But 30K will cost you thousands of dollars in those days. So there's no video RAM. So how do we draw something in the screen? We will learn soon. It has a register-like model. We'll know in an example what that means. You will see code soon, no worries. And it has a clock as well. And this number is super important. The clock runs at 3.53 megahertz. That is around 3 times. It's not exactly, but around 3 times the CPU clock. So the important thing here that I want you to know is that one TIA clock is 3 CPU clocks. Okay? What is the number? It doesn't matter much, but that reasoning of 1, 3 is important. We have the video card, we have everything. Now we need to put things in on a screen. And for that, we have the CRT TV that exists in those days. Again, like the joystick, if you don't know what that is, ask your parent, right? Because I would feel even older than I am if I have to explain it. But TVs in those days were super metal, man. The way that just draw things in the screen is shooting electrons to a screen. Like a rifle shooting electrons. I know an expert in how this works, but the important thing that you need to know here is that for color TV, there is a frequency that you need. That is 3.57. And this is why the TIA has that frequency, because it has to just go accord to the wave in the TV, right? Sadly, the frequency is not a standard, and we will see that in a second. And how do we draw things? Now we know that it's electrons. Well, because you are shooting electrons, you have first to warm up the gun, right? And warm up the gun takes around 10.9 microseconds. And once you warm up, it starts shooting electrons from left to right. And drawing the whole screen takes around 52 microseconds. And once you do that, you have to turn off the gun, return it to your left, and do it again around 480 times. Right? So we call that the resolution of your TV, 480 lines, and it's an approximated. Why? Because manufacturers never agree in a number, right? That's another constraint for you, my friends. Right now you talk about pixels. In those days, you don't even know how many lines you have to draw something, because it could be around 480. Who knows? There were cases where the same manufacturer in the same TV has different line numbers. And once you get to the bottom, you have to turn off the stuff and just send it to the top. That takes around 45 lines, around approximate. Okay, now let's do something. I'm not a mathematician. But if we take the frequency that I said, 3.57, and divide it by the time that it has, that means that it will do 68 jumps while in the warm-up zone. These jumps are called color clicks or color clocks, right? From now on, I'm going to call it pixels, but they were not really pixels. That's just that the frequency means that it just jumped from one side to the other, right? So 68 color clocks, 160 color clocks for drawing the screen, and because 480 is too much, you divide that for around 2.5, you have a total of around 192 lines, right? Now there's one number that I told you, and I hope that you remember, that is that you have 3 CPU clocks for 1 TIA clock. Let's call the CPU clocks cycles, and let's call the TIA clocks, or pixels. That means that during warm-up, I only have 23 CPU cycles. And during drawing the screen, I only have around 53. That means, ladies and gentlemen, oh, where are you? Yeah. That you only have 76 CPU cycles to draw a line. And if you remember, instructions can take between 2 and 7 cycles. So it means that you have very limited set of instructions that you can put to draw a line. That's the constraint that I like. Because now we're talking about like challenge. The boss enters, you are entering the dungeon now, right? And that was not one of the biggest problems, because not everybody made the same TV. There were overall 3 standards: NTSC, PAL, and SECAM. Nobody used SECAM. That thing is just forget about it. And the variation is not only the number of colors. PAL, for example, has more colors, but the frequency. PAL has better resolution, but the frame rate is lower. So that's why people that is obsessed with retro gaming thinks that we Europeans are pretty slow, because our games actually were slower than the games that they play in Japan and United States, because the frequency. Okay, we have our rules. Let's draw the screen. Let's see some code. Remember that I mentioned the other game that I love, or the people love in those days, that was Tank. Pretty simplistic game, that was Tank. Please raise your hand, whoever played Tank. Yeah! So, How do we handle that? Let's see. This is time, right? Without the shooting and things like that. So the first thing that you notice is that we have a background. To put a background, and I said that is a register, we start with the background. Let's start off with red. And these are the two instructions to change the background. You change the background for the whole thing, right? This is 6502 assembly. I'm not here to teach, but those two instructions, the first one loads a value in the register A, and the second put the value of that register A in a memory area. And the memory area here is 9. That is where controls the background color. I'm going to be talking about setting registry. When I said setting registry, it's pretty much this. These two instructions. You consume 5 cycles there, by the way. Those two instructions are 5 cycles. 2 cycles for the first and 3 cycles for the second. And STA, depending on where you are putting the memory, can take up to 7 cycles. So we put everything in red. So let's see, what else? Now that we have the background, let's make the maze and the whole stuff, right? How do we draw this? Again, you have limitations. In this case, mechanical limitations. Because it's 1975, it's a very cheap product. What can we do here? If you put attention to this, you will notice something interesting. That the left is the same as the right, but mirrored. Obviously, this was a programmable pawn machine that was designed for the same boring games that everybody was playing in 1975. So that's why this was a very good limitation. In 2600, you only can draw half of the screen. The other half is a copy of, like the right is the copy of the left. So you never draw the whole screen. How do you do this first? You have 2 modes, exact copy, that basically is this 1, 2, 3, 1, 2, 3, or mirror, that is 1, 2, 3, 3, 2, 1. Right? So only those 2 modes. But the important thing here is the left is the same as the right. Always. The same registries. And for that, you set this registry. Again, this is a pattern that we will see. When I say set registries, this is what we do. Again, 5 cycles here. Right? So it means that we only have to worry about this. And Atari will take care of everything else. How do we do this? Okay. You have 20 bytes to do this. 2 registry of 8 and half of the registry that takes 4. So we call that pixels, or like logical pixels. So you have what is called a playfield of 20 pixels. And you set the values for those things in the registry PF0, PF1, and PF2. And if you think about that, one way to do that is with 0s and 1. For example, I want to draw an H. I just put a bit when I need to put in the pixel, and it will draw that thing, right? And I can define that pattern in the code as a sequence of bytes. And that means that I can do it. Now I solved this problem. In fact, it's so cool that if you just continue looking at this, I could actually draw only the top and then draw the bottom in the opposite order. And that's what we could do in code. It's not important that you read this, but this is actually how we will do it. We just put a loop, count from 1 to half of the screen, and then in reverse order, reading from the bytes. We solved it, isn't it? Wait. That takes 86 cycles. How much do I say that cycles we have per line? 76. We are over 10 cycles. What do we do? Simple solution, my friend. They said people is not going to notice the difference, so instead of using one line, we are going to use two. So it's very common, and most of the games we're doing what is called a 2 or 3 line kernel. So it means that you just draw 2 lines instead of 1. So that means you have 176, 154 cycles to just play with. And woohoo, we solved that problem and we have more instructions that we can show. Pretty awesome, right? Again, you see the constraint, you see how to solve it. And this didn't stop people to do amazing things. For example, this is one of my favorite games for the 2600. It's Atlantis. And when you start looking at these patterns that I said, you can notice that now the left is the same as the right. And that's a reason for that. And now you know why. It's an exact copy, not a mirror copy, but that's how. Everything else is just adding the other stuff that you see there. But there is a problem. There's always a problem. People want more and more, especially managers. So what happened with this? This is the infamous ET, right? That, by the way, didn't kill the industry as everybody said. It was no ET, it was management. Good thing, when Bushnell left, the CEO of Coca-Cola in those days was the one who took Atari, and he got interviewed about why there were more copies, they were making more copies of the ET game than the number of Atari consoles that they had. And he answered back, that is so good that people is going to buy one for each room. So left is no different than right. How do we solve this, right? So they came up with a solution. Remember that I said that there are 3 registries? So I set the first 3 registries in the H blank or whatever when we start and all of that, right? And then we start drawing the screen. But what we do is that in the moment that we finish drawing the first part, we set the content of the first part, or we override what we have. So that means that the next time that it gets to the half of the screen, it will be a fresh registry to do it. And then when we finish drawing the second part, we set the next registry, and so on. So it was clever. In that way, you can have like what is called complex playgrounds, as they are called. And this is a technique that is so common and so abused by almost every game that has a name and characterized the 2600. And it's called raising the beam. Because you're constantly coding to just be faster than that electron rifle that is shooting electrons. You are racing against it. So you reorder your instructions to just do those effects.
Does that mean that they needed to work out how many cycles would have elapsed?
Yep, you are constantly counting. You are constantly counting in your code. Actually, like Current, you can install in VS Code or there's a compiler, an online compiler for 2600, and it tells you the cost of each line. So you can just see, because this is important. You are constantly counting to know how and you reorder the instructions to do it. Today, the compiler does most of it for you. If you learn computer architectures and things like that, that is something that most compilers do, because they have to reorder instructions to support pipelining and things like that. This allows us to do fantastic things like this. This is Ada Lovelace written draw in 2600. Pretty good resolution, pretty good everything. But you remember how we have to put the pattern? we have to describe the bytes in our game cartridge to do this. And that takes a space. And you only have 4 kilobytes for your code. Remember those 8 kilobytes that I told you? You don't have all of it. You only have 4 kilobytes for your code. And that caused a lot of problems. For example, Pac-Man, the guy when he wrote Pac-Man for 2600, he was accounting that he has a 4 kilobyte cartridge, and just 4 weeks before releasing Pac-Man, it was said that they want to reuse the 2 kilobytes that were left over, so he has to remove code to fit in a 2 kilobyte cartridge. Sometimes management is the constraint. Right? So, no worries, we are just doing this. Now what we need is the score. For example, to do the score, there is a mode for the score, and it's called score mode. They were not very creative with the names. And the way you just set that in a registry to put in a score in the score mode. And then you have to raise the bin. Now you know what that means, right? You have to raise the bin to write the numbers. Left and right, the same characteristic, the same stuff. And you have the numbers usually as a pattern in your code. Now we have what is called the background, the score. It's time to have the character. I'm not a graphic designer, but I will say that there is a big difference between Pitfall Harry, from Pitfall, a really good game, and Belfort from Castlevania. The difference in them is around like 7, 8 years, because one is pixels, the other is lines. If you put attention, they are lines. There are no vertical differences, they are lines. Because what you draw is lines. Remember, lines, not pixels, lines. So the character is easy. It has 8-bit registries. You have 2, one for player 1, one for player 2. The only thing that you can change in your character is the color. And to display it, you only can display it or not display it, right? Just can't turn it on or off. And you have like a few nifty things, like for example, a registry to stretch, just do magic things. Let's call it effects. In your player object, in your bitmap for the player, and just revert it or not. Some games actually took advantage of it. Like for example, this is one of the modes for air combat. Basically, that's why you see 3 there, because now you only have to draw 1 airplane, and it's just triplicated thanks to the TIA registry that you use.
Why don't they make 3 separate players for each of the enemies?
Because it costs. Because CPU cycles. But, you remember what I say about raising the bin? You can raise the bin. You can do the raising the bin as well with the player object. So now you can do magical things, and we will see how they did it. A few of the stuff. The talk is nearly there, but it's going to be over, and you will see like nifty tricks there. Positioning is another problem, because as I said, you can only turn on and off the player. So that means that if you count from top to bottom all the lines, your player will jump in 15 pixels. So it will be here and then just later. And that's the worst FPS ever seen. The frame rate was terrible. Right? So to solve this, you have another registry when you can just adjust the position up to 50, like 15 more to the left, like 7 more to the left, or 8 more to the right. Right? Everything's registry, as I said. This didn't stop to do magnificent things. This is Donkey Kong. This is Donkey Kong for 2600. And if you notice, we have players. The way that this was done is that Donkey Kong and, I don't know, the princess is player 1 and player 2. That you just draw when you are in those lines, and then reset, and Mario is player 1, and each of the flames is player 2. But how we can do this? You cannot see it here, but what you do is that you start alternating between them. Like, again, raise the beam, but now not only horizontally, but vertically.
Is Donkey Kong moving only when Mario is?
Yeah.
Because of that trick? Okay.
Yeah. You start noticing things like this because it's shortcuts that they take to do this, right? That's why. Because Mario is moving vertically, so it means that it's enough time to just draw the next step. So, and the last is missile and ball. This is very simple. There's no patterns for them. They are very similar, and they're only 1 pixel in size. And the only thing that you can make is make it bigger or smaller. But actually, that didn't stop people to do amazing things. For example, this is basketball. This was released in 1979. Right? And one thing that I like that I don't think that that here is shown is that there has a 3D effect for the ball. That sometimes you throw the ball outside and the ball is going to be bigger and smaller, like because it's going to the player's face. The way that they did that was just using the registry to make the ball bigger and smaller. So that's pretty neat as well. Again, think about this. It's just about like, not even creativity. It's just like, oh man, how I do this? And most of these developers, when they're writing their stuff, it's like, you know what would be cool? Adding this effect. I think I can do it. And things like that. And the missile was just 1 bit. Here is positioned very, very fine and calculated to just follow the player in Jar's attack. One interesting thing about Jar's attack that you see here is that pattern that you see in the middle. Did you notice that I never said that there was a random number generator in the Atari? There wasn't. So how do you make that pattern? That pattern is the code. That pattern is the code. They basically like read the code and see how is what they are reading while it's executing, and that gives you the impression that it's random. When you mix all of this together, you have sometimes things that are awful, like this. Pac-Man, 1981. Let's try to guess what is happened. And the reason is very simple. You only have 2 players, right? Pac-Man is player 1, and 1 ghost is player 2. But you can have up to 4 ghosts. What do? You render one in frame 1, render the other in frame 2, and so on. So that's why they flicker. Because they are not rendered at the same time. In fact, the big pills in the corner are balls that renders every 3 frames. If you notice, the balls are not rendered all at the same time. And now that you know all these type of tricks, there are many more that developer has done. I recommend you to just start looking at Atari games. I just start noticing like, man, how did they did this, right? So the lesson is constraints and how difficult was hardware and all the things that they have to do. Sometimes inspire creativity and just make you do pretty awesome tricks to just overcome those things. If you want to go after this and write your own Atari game, be welcome. You can actually even print it in a cartridge and everything. This is important because it's 2025 May, I think it's already. There have been just up to last week that I checked, 35 new published games for Atari, printed in cartridge, physically. And last year there were 60 something. So there's still people making games for this console because it's how inspiring there is. It's like you think that you can do it. And this happened already to a person that actually published a game already, not for Atari, the vice president of Xbox many years ago. After Halo was released, he just took 1 week off and learned about the Atari and made Halo for the Atari 2600. And it's a great game. It's published and everything. Obviously, it's primitive. I'm old school, but not that old school. Right? So, finally, if you want to get more into this, I have a few recommendations for you to read. The first, the classic book, Raising the Bean, by Montfort and Bogost. It's not that dense, but I really like because it's full of really catch-up stories about how they overcome all this stuff. There's a story about like how they founded Atari and all the problems that they stuff and the fall of Atari, because there were like a big problems at the end of it. So I really recommend that book. Another book that I recommend is a little more complicated, is Making Games for the Atari 2600 by Stephen Hawk. It's a little dense. I recommend first Raising the Bean and then read this, right? And the only thing that I tell you is, after reading this book, probably you will end up buying a 2600. Yeah. And finally, so you know how people is obsessed with this. You think I am obsessed with this? No. This guy published a paper just a few years ago about the archaeology of an Atari game. He basically disassembled the game, and this is a 15 pages paper explaining how they use tricky algorithms to do like that. They were doing image compression in 1983, right? And how they overcome all of these things. It's a really good paper, really good reading, but it's an academic paper. So if you are like me into that type of shit, go and try it, right? And that's all that I have for you. If you want, we can just discuss and talk more about 8260, like old CPU programming out there, or games and things like that. Thank you very much for coming to my talk. I think we have 1 minute for question or no.
Could you go back to that article URL?
Yeah, sure.
About 6 minutes.
I have 6 minutes. Wow!
Constraints.
Constraints, man. Yeah, any question?
What's the most like complex game, in your opinion, on the Atari?
One thing that you notice in consoles and video game history, and you don't need to be old like me to see it, you see it from the Xbox, is that the games that are released at the beginning are okayish, but the best games from all the characteristics and things like that are at the end, right? So you can notice this, and if we talk about the classic one, the classic game, I would say Solaris. Solaris is a game that was released in the NDC Activision game releasing, I think that was in 1985, 1986, for the 2600. And when you see it, it doesn't look like a 2600 game. It looks like a Nintendo game, right? Because it was 32 kilobytes. And then you're going to say like, hey, Cristian, wait a minute. You said that only 4 kilobytes of code. They did like really crazy stuff to just start jumping between pages to load things dynamically before they appear, right? And the sprites and things like that, they just warm the sprite outside the rendering zone. So they just appear. It's fantastic. In my opinion, I love the game as well. It's one of the most complex pieces of art done. Solaris by Activision. Sadly, I don't have a screenshot of that one, but yeah, it's really good. It's really nice. The other that I will set is, it's not Formula One. There's like this racing that happened between Europe and Africa. What was the name? Dakar. Yeah, there's a Dakar game as well that basically has curves and everything. And just imagine the curves are like playfields. Imagine rendering that what your car are doing, like very complex. We even like background of the city with the sun going up and down. And sometimes you are at dark and you only see the city lights and the lights of the cars that are coming. It's another really good game with like a lot of tricks. So yeah, I would say those two.
Thank you.
They were released at the end, but again, it's this. They were released at the end of the console age. I said the end because the console actually stopped being produced until 1992. So think about that. 2600 just has such a long lifespan that it was produced in 1992. But they were like crazy Brazilians that they just like continue producing it because it got licensed to a company there and they just continue making it until 1992. Yep. Any other question? I know you have questions. Don't be shy. Come on.
So you mentioned the 32K cartridge thing. Were the cartridges active in some way as well? Like, did they have
not like the ones,
electronics?
not like the ones from the Super Nintendo. That was very common to just put chips, special chips, there to just act things. For example, the first 3D game was Star Fox for Super Nintendo that they put on a specific chip to just give all the effects. Not here, because you can't. Remember that they cut lines, so you will need those lines to go to the CPU to support that. In theory, you could do it, but only with the consoles that I mentioned that were made in Brazil. Because the consoles made in Brazil, they actually use the 6205. That is just a new version of the 6202. So they have actually the 40 lines. In fact, it's interesting because for many years we thought that you could not reset the 2600, but that Brazilian console, the version, you can reset because they didn't cut the lines. So they have the reset line.
So that game would only work on one of those
Yeah.
consoles.
That's important as well because Atari released the third console. The second console was a big flop, was the 5200. The third console is the 7800. They made it compatible with the 2600. And there are certain games that because the racing that being stopped that it does, that cannot be played in the 2600. And there are like modern games that you can just make to only play, that there are 2600 games, but only will play in the 7800. So it's like constant trade-offs.
Do those have faster clock cycle too? Or do they keep the same?
Keep the same. Yeah, they actually have the same CPU cycle, but the difference is that since the 5200, they actually put a buffer to handle sprites and background and things like that. So the 5200 start doing. They have to do this because one of the competitors was Coleco, and ColecoVision actually like prices were different in 1979, and they have enough money to put memory for a buffer for graphics. So they have to, there's a saying, keep up with the Jordans, I guess.
You mentioned they stopped making them in, was it 92?
Like the 2600, yes, in Brazil in 1992.
Okay. You also said when you read that book you're going to want to buy one. Is this an eBay for $12,000 situation?
No, actually no. 2600 is one of the, I collect consoles and I have many, right? I don't have a full Atari collection because it won't fit in my house because they made over 500 games, official games. No, there was no anti-pirating and stuff in those days. So there were so many pirate versions that if somebody tells you I have the whole Atari collection, just don't believe it, because that shit is going to be like thousands of games. Atari games is too old school, so it's not that popular. I buy games in eBay that for only €5, for example. I bought my wife actually got me my 2600 here in Australia, and obviously she never told me how much it cost, but I'm pretty sure that it was not an iron and a leg. So it's a good console to start experimenting. The only thing is that need to be careful, because the way to connect to the TV was very different in those days. So some people sell it like modded, and it worked. Supposedly, Atari is going to release kind of an FP3A this year, so you can play 7800 and 3600. So supposedly this year, I don't know. But now it starts and things like that, so who knows. We ran out of time. Thank you very much for coming.